Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone in the audience here and the virtual audience who are looking over the internet. It's my pleasure to welcome Yasu Furukawa, who is a graduate student at the University of Illinois Urbana-Champaign. Yasu has developed some of the nicest multi-view stereo reconstruction algorithms out there that take a variety of photographs and build highly accurate 3D models, and he's going to tell us about that work.
Yeah, thanks, Rick. Thanks everybody for coming. I'm Yasutaka Furukawa, and I'll be talking about the image-based modeling, or multi-view stereo. And this is joint work with my advisor, Jan Pans. So first of all, what is image-based modeling? It's about reconstruct 3D geometric information from images. Of course, there are whole different kinds of vision algorithm which use images to do 3D reconstruction. But we focus on a problem which is often called a multiple view stereopsis or multi-view stereo. So the problem is, take pictures of whole different kinds of objects. It could be some like a toy like this, or some statue, or a face, or some skull. So for this data set, some anthropologists at my university interested in analyzing the structures of these skulls for human species, ancient human species. So they brought this data set to our group. And also the image may contain more like buildings instead of the objects. And also the images may contain some obstacle, like pedestrians. So in this situation, you take pictures of the building from different viewpoints. Then you want to ignore these regions. Then just reconstruct the building structures. So more formally, we focus on a problem that takes a set of images and camera parameters. So assume that the camera parameters are given. So there's a well-established structure from motion algorithm that takes images and give you camera parameters. So we're not going to touch that part. So assume that the camera parameters nicely are given. Then we are going to reconstruct 3D geometry of objects or scenes that are rigid with respect to the cameras. So this rigid is a kind of key to handle pedestrians in the previous slide. For the building with pedestrians, if you take, for example, 3 images, so probably the building is still there, doesn't move, but people probably move. So people are not rigid in the 3D scene, while buildings are rigid in the 3D scene. So that's why we like to define pedestrian as an obstacle, and we ignore that. So you're going to ignore whatever object which is not rigid in the 3D scene. Then this is kind of our typical input and output. This is input for images of my face. There's actually some projection patterns on my face. Then this is a 3D mesh model that we get. So typical input output. Oh, by the way, so feel free to stop me and ask any questions at any time. So I'd like to mention why we like to solve this problem, because they are important. And first of all, in comparison to later range scanner-based methods, which is kind of popular for graphics, first of all, the devices are cheap if you use image-based modeling methods, cameras. And you have many pixels and reasonably priced. And the price is the one big advantage. And the other advantage is the number of pixels you get from the device. Or in other words, lateral resolutions are high for cameras as opposed to a laser range scanner. And also cameras are fast, higher frame rates, and which makes our image-based modeling algorithm handle a different kinds of data sets, which laser range scanner can't handle. And I'll give you some example soon. But the disadvantage is, again, the accuracy of estimation, or vertical resolution. And thanks to some quantitative evaluation of image-based modeling methods, a multi-view stereo algorithm, which Rick is also involved, and Steve Seitz and other colleagues. So according to their evaluation, kind of state-of-the-art multi-view stereo algorithm gives you an accuracy of about 0.5 millimeter on about object of 15 centimeter in diameter from a set of 640 by 480 relatively low resolution images. Well, if you pick one like a laser range scanner model, which costs about $15,000, according to their spec, their depth map is guaranteed to give you 0.1 millimeter accuracy. But one thing to note is this is coming from just a low resolution images. You can just buy 12 megapixel if you have enough money. And that image is 4,000 by 3,000. So probably makes this number much better. And also for this number, this is just our specification for a single depth map. And typically if you want to have a single 3D model, you have to scan from multiple viewpoints. Then somehow fuse our multiple depth map into a single 3D model, which may introduce maybe some more additional noise or some manual work, while image-based modeling is kind of fully automatic. And I'd like to mention a couple of examples where we can handle, but later in this scanner can't handle. One example is some asteroid movie. If you go to NASA website, you can actually download an asteroid moving in the space. And ideally, you can probably just use structure for motion to get some camera parameters and run the multi-view stereo reconstruction. I guess it's kind of hard to use laser image scanner to do the same thing. Maybe really expensive, maybe too long, take forever until the light comes back. And another situation is like a fast-moving object, like a baby. So if you want to scan some baby, you can't say sit still. So you can use laser image scanner to get the digital like cloning. Or you can set up like multiple cameras to fire at the same time to get the 3D reconstruction of a baby, like face or body. And the really extreme example is in this picture you see kind of famous kind of stone step on a cultural heritage thing, and which has been eroded for years, like wind or rains. And some people are interested in getting the structure 100 years ago. And you cannot use laser scanner to get the structure of these stone steps 100 years ago, because there was no such device a long time ago, and you don't have time machine to ship the laser scanner at that time. But there actually exist some images which were taken a long time ago. And actually, we use that image to do 3D reconstruction for this data set, and you know the structure 100 years ago. So there are some situations where we can handle, but laser image scanner can't handle. That's why we like to kind of solve this problem. So here's the overflow for the rest of my talk. First, I'm going to talk about the thing called photometric consistency function. It's kind of more introduction to people who doesn't know like reconstruction, multi-view stereo, kind of key concept. Then talk about many ideas of our approach and detailing the algorithm, and show some results and talk about some future work. So first, photo consistency function. So the basic idea of how to estimate depth from the multi-view is just what we do with two eyes. You cover one eye, you don't have a good sense of the depth, but we have two eyes, you can kind of do some triangulation to estimate depth. So multi-view stereo is all about this kind of triangulation. But we look at this kind of property in a slightly different way. Suppose in this toy example, you have like 3 cameras, and you're looking at the surface. Of course, you don't know the surface. This is something you're not trying to reconstruct. Then this photo consistency function is, this function takes some 3D coordinate, or you give some 3D point, then you get some scalar value back. And if the scalar value is small, which means that point is likely to be on the surface of an object. Well, if that function value is high, then that point is not on the surface of an object. Probably it's still not clear. So I'll give you one simple example of such a function. So suppose in this situation, you like to evaluate such a function value, for the consistency function value for this 3D coordinate. So what we do is, since you know camera parameters, you can just project this 3D coordinate into each image, like this. So you can just look up the pixel colors at these image projections. And we expect those 3 pixel colors to be different because this pixel color is coming from this 3D point on the surface of the object, while this pixel color is coming from this point on the surface of the object. So those 3 colors should be kind of different, not similar. While if you are trying to evaluate the function value at this 3D coordinate, which happens to be on the surface of an object, so what we do is project this 3D coordinate into each image, then you compare those pixel colors. So they are probably similar because they're coming from the same physical 3D point. So for example, by computing a variance of those pixel colors, and if you get smaller value, which means the point is likely to be on the surface of an object. So naively, what you can do is have 3 cameras, just sample 3D points in whole space and evaluate function value. Then what you should expect is something like this. You get smaller values here where the surface actually exists, and higher value in the other places. So our problem is, in that sense, trying to find a 2D surface where this function, for the consistency function, is small. I hope, this makes sense. So talk about the main ideas of our approach. I guess there are a couple of more main ideas, but I just picked 3 here. The first idea is patch-based surface model, which is probably if you hear about like reconstruction or model, you probably think of like a mesh model, like a triangulated mesh model. But in our work, we use a bunch of small rectangle planar patches to represent the surface of an object. So if you look at this video, let me play it again. You're looking at just a bunch of small planar patches with some texture mapped on. So these are covering the surface of an object. We use this set of patches to represent the surface of an object instead of a triangulated mesh. So each patch, basically you just want to know the center or the position of a patch, which we like a center C of P for each patch P. You like to know the 3D coordinate of the center of a patch, and also the normal, the orientation of a patch. So these are kind of two parameters you want to estimate for each patch. And the size of the patch actually is automatically determined. We pretty much rescale the patch's rectangle so that its image projection is always like 5 by 5 or 7 by 7 pixel according to some user given parameter. So the problem is basically to find those patches. And for each patch, you need to estimate these two parameters, location and orientation. Then what we do is, in this again, two examples, we have some surface here. Then suppose somehow you can initialize a patch. You can initialize, so this is the, for the consistency function value, you can actually compute. And what we do is somehow we initialize these two parameters, kind of guessing that patch may be here. What we can do is kind of optimize these two parameters, kind of pushing this patch towards this local minima. So we can simply just optimize these two parameters so that this kind of function value becomes the minimum. So this is kind of typical optimization problem. We have function to minimize. We have parameters, two parameters, and location and orientation. So what we basically do is initialize these two parameters and use some optimization package, whichever optimization package you want, and to refine these two values. And I'll talk about how we actually do here later. But this is the kind of main idea of our approach. And second idea is kind of related to how to initialize those patches. And we do some expansion procedure, which is typically surface is smooth, like this. So suppose you get one patch reconstruct at the right place. So we expect another patch to be like left and right here. So we can kind of expanding patches on this plane instead of exhaustively searching in the whole 3D space. So there's some smart strategy about searching in 3D space. And this is kind of second main idea. Again, I'll talk about the details later. The third main idea is how to handle occlusions. So in this example, again, this is actually the real data set only from 3 images. So if you want to compute 3D structure here, you like to use only second and third image while ignoring the first to do 3D reconstruction. So the problem is you want to compute photo consistency, but you don't want to use the first image. You just want to use second and third to compute photo consistency. And how we do it is actually really simple. So suppose you have some patch, and you're now trying to evaluate photo consistency function value. So these projects down to suppose these 3 locations, and you don't want to use this image to compute photo consistency. And the trick is really simple. So we simply compare textures. So first we compare these two textures that look different. And these two textures, again, image region look different. Well, these two look similar. So before computing photo consistency, we kind of try to compare those image regions and detect outliers. So there's some kind of hacky condition, which one is our false outlier, inlier. So before doing photo consistency computation, we detect outliers. So this one looks different from all the others, so we ignore it. Then compute photo consistency by using only inliers. It's a really kind of simple trick. Yeah.
How do you compare the patches?
So this, you just compare image regions. So typically we just compute the normalized cross correlation between those image regions. Then, so in this example, you have bad photo consistency, normalized cross correlation value for these two. Well, this one has a better one with the third image. So this one has bad photo consistency for all the others. So we can tell that this is outlier. And the actual condition is a little bit more hacky. So I'm not going to talk about the detail, but the idea is, compare textures. Basically comparing the normalized cross correlation, between image regions, and detect outliers.
So how many images at a time will you be trying to match?
As many as possible.
Okay.
But there's some computational reason. You don't want to use like 100 images to compute, patch. Mm-hmm. And typically, maximum is, I guess, 10.
Okay.
The minimum is 3.
So if you have 10, would you do, the 10 choose 2 possible pairwise photo consistency scores and then rank them and then do some kind of
Yeah, that's right. Yeah.
Okay, so it's quadratic in the number
Yeah, that's
of images
right.
that matches.
So the maximum number of images we use is really like a bottleneck. You really change the running time.
Yeah.
So you don't want to want that to be too large.
Okay.
And the minimum is important. So you want to have at least so in this example there are 2 images which are consistent. Mm-hmm. But typically I just enforce that there must be at least 3 images which are consistent. And which makes things kind of robust. Mm-hmm. But in this example because there are only 3 images, I cannot set the minimum to be 3 to handle occlusion. So in this example I set that value to be 2.
Just one more question.
Yeah.
You assume the camera is already calibrated.
Yeah, that's right. Yeah, camera parameters are given. So that's why if you know you have the patch in 3D, you know where that should be visible in each image. So I'll detail in the algorithm, which consists of our 3 steps. So first, we detect features in each image, and using 2 popular feature detector, the Harris corner detector, which is supposed to detect corner-like features, then difference of Gaussian, which is supposed to detect blob-like features. Then we just detect 2 types of features. This is another image from the same data set. So we detect the kind of dense features. In the second step, we try to match those features to generate a sparse initial set of patches. And here's some toy example. We have 3 images. Then in the first step, we detect features in all the images. In this step, we are trying to match. Suppose if you pick one feature and try to match this feature to another feature in another image. And if you know camera parameters, there's a thing called epipolar line, which is, this feature must match some feature or point along this line. You don't have to search in the whole 2D image to match features. So what we do is we kind of look at the feature near this epipolar line. And suppose you find one feature. Now we are trying to match these 2 features to generate a one patch. Then, so if you believe these 2 features match, you can actually already compute the location of a patch approximately, because you have 2 images in 2 cameras, the camera parameters, and image coordinates. So just shooting rays, a intersection. Then you can initialize the location of a patch from a triangulation. Then you can initialize another parameter, the normal orientation, by simply taking the optical axis of one camera, kind of assuming front parallel patch or front parallel surface. Then we are going to refine these parameters while minimizing a photometric function. Then, so before doing that, since we know the location of the patch approximately, we can also predict where this patch should be visible in the third image. So because we are trying to use as many images as possible to compute for the consistency. So we now know that these 3 features may match. Then what we do is what I have just explained before, detect outliers, then use only inliers to compute for our consistency. So here, the patch slightly changes orientation location. We use some optimization package, actually just conjugate gradient, a nonlinear conjugate gradient, to optimize these 2 parameters while minimizing the function. So we get. So after this optimization, if the for the consistency function value is below some threshold, then we take it as a success, otherwise failure. So suppose in this example that was a success, so we mark like these regions kind of gray. We are not going to touch that gray area, and we keep on doing. Again, pick another feature, epipolar line, and trying to match. Same thing again and again. And by the way, this cell is our beta by beta pixel cells, and beta is some user input parameter. This controls the density of the reconstruction. So our algorithm tries to reconstruct at least single patch in every beta by beta pixel cell. So if you want a really dense reconstruction, we set beta to be 1, which is you want to get a single patch in every single pixel. But typically we set this value to be 2 or 4, which means you want to have a single patch in every 2 by 2 pixel in the image domain. So again, do some optimization. Well, this one actually shouldn't move in this step. There's some inconsistency. Yeah.
So this set of features here is different from the set of features used from the structure for motion?
So I would say similar. But I think if you run structure from motion, you don't know camera parameter in the situation. So you really want to use significant features. But in our situation, because you have camera parameters and epipolar are constrained, so our features basically use similar feature detector, but are more dense. And we do not really care about the significant feature. We get it doesn't look like a feature, like in this figure, but we just want to cover the whole surface. And so I would say detection schemes are similar, but we kind of more aggressive about detecting features in the whole image. Is it answering your question? Yeah.
So you greedily process one feature at a time?
Mm-hmm. Yeah, I'll pick one feature one by one.
There's no coupling between the features? You don't just
No. There's one thing so suppose you get this patch reconstruct, we mark this cell gray, which means we're not going to pick a feature from this cell anymore. It's kind of a way to control not duplicating results again and again.
You're not guaranteed to have a feature for each beta pixel, right?
Sorry?
You're not guaranteed to have a feature in each beta pixel?
Actually, when we run feature detector, we enforce that we have to detect our I think a single feature in like every beta by beta pixel.
Okay.
But sometimes you do not get many feature in a cell.
Yeah, yeah.
So because after running the feature detector, we first look up the local minima of the response. If there's no local minima, local maxima in the response, we are not going to get any features. But we have some framework to cover those area in the third step of the algorithm.
But you
So
don't have to have any feature, right? I mean, if you
Look at a piece of paper from the front and from the
Yeah.
side. You're not going to get.
yeah, that's right.
you
So
can't
we are
fix it, right?
screwed. Or yes, hope that there's some shading in the paper.
It's a paper, right?
Yeah, yeah.
You look from the side, all the features match.
Oh, I mean 90 degrees, then you can see,
Yeah, whatever.
yeah, so we give up
Even 45.
or use another approach, maybe structure from silhouette.
It doesn't exist, right?
Yeah. So in that case, yeah, we can't do anything. Well, maybe any other multi-bit theory can't do anything.
So would you say then almost your feature detector is a way of just making a sparse search along the upper line?
Yeah, that's right. Then we are going to make it dense in the last step. Let's see, where have we? Oh, here. Oops. So we have come with the second step. So after this step, we get some sparse set of patches. But probably you have seen the algorithm was really naive in the second step. So it makes lots of mistakes. So in detail, it's like throwing a bunch of patches in the 3D space, and without worrying too much about false positive or false negative. Just throwing a bunch of patches in the 3D space. So it makes mistakes and also kind of sparse. So in the last step, you like to make the patch dense and also can filter out bad patches or incorrect patches. So first of all, the expansion procedure to make it dense. So what we do is this is the second idea I explained before. So this is something we expect on the surface. You have some smooth surface, all the patches are lined up nicely. So what we do is, suppose you have one patch reconstructed from the second step, initial feature matching phase. So what we expect is, there should be a patch here and there. So we initialize two patches here on the same patch plane because we estimate surface normal. So we expect another patch to be here and there. So we initialize the normal orientation by just copying the normal. And the location should be on the same patch plane. So we initialize these two parameters and again run optimization, minimizing the photo consistency function. Then here you get green. So we keep on doing that again, pick this one, then again initialize it and refine, optimize. So we keep on doing that until you cannot do anything. So this is an approach to make it dense. And for filtering, you have to remove bad patches. And you see two typical situations where bad patches occur. Suppose you have in the left diagram, you have 4 cameras and you have 4 patches, 4 correct patches, and 1 incorrect patch. So kind of floating in front of the correct surface. So what we can tell is, so suppose you get this patch P1, where you refine patch P1. We use image I4 to compute photo consistency, which means patch P1 think that I should be visible in camera I4, but P0 is blocking. And if you look at the patch P2, patch P2 thinks that I should be visible in camera I3, but patch P0 is blocking. So there are a couple of patches which are conflicting visibility information. So what we do is for each patch, we collect a set of patches that conflict in visibility information. Then look at these patches to decide if the patch is erroneous or not. Then in this situation, you have single patch and 4 patches complain altogether. So this one is likely to be an outlier or incorrect patch. So basically compare some photo consistency function value here, all 4. There's some kind of hacky condition to tell this outlier or not. So we can remove. And in the right case, same thing happens. Suppose incorrect patch lies inside of the true surface. Again, same thing. You detect, find a set of patches which conflict in visibility information. Again, do some comparison to detect outlier. So this is kind of summary of what has happened from the first to the third step. So in the first step, you detect features. And in the second step, you match those features to get a kind of sparse set of patches. There are some incorrect patches. In expansion, we get results like this. So we hope that this surface to be covered. And you may get some additional incorrect patch as a result of expansion. So what we run filtering to remove these bad patches, like here. And we may accidentally remove this bad patch. But we apply expansion filtering a couple of times, 2 or 3 times. So this one is going to be covered by the next expansion step to get a kind of final patches. So now let's show you some of the results. Oops. Yeah, here. Here the data sets are object data sets have been tested. Typically, the images are 15 or 16, maybe 20, 30. And these two are like 4 images and kind of latest data sets. So initially, I didn't realize that you need many images. I didn't realize that we can do a good reconstruction from only a few number of images. So this is kind of dense. But these examples show that from only 4 images, you can get really good reconstruction, which you'll see in a minute. And here is the, let me stop one movie. It's not powerful enough to play both. Yeah. So you're now looking at the bunch of patches with a texture mapped on. But because they are so tiny and dense, it doesn't look like just independent patches. Here. Here's again just a bunch of patches. But of course, you want to get some mesh model from patches. So you have to go from patches to a mesh model. And so we do that. So there are a couple of methods which takes our set of patches oriented point set into a mesh model. Actually, one of your Hughes work. There's some actually library or program we can use. Just give oriented point sets and get 2D manifold. Or there's another approach by Professor Coles or Michael Goesele, which is actually originally designed for laser range scanner based methods. But probably you can use a similar technique to convert from patches to a surface model. And we'll end up using is a more hacky one because it was kind of easy to implement. What we have done is we somehow initialize a mesh model. So if we have our segmentation information, we can use our visual hull to initialize a mesh model. Or if you don't have such a segmentation like a building structure, then you just use a convex hull of reconstructed patches to kind of initialize a mesh model. Or maybe something more. Then after this, or in the case of visual hull, you get some visual hull mesh. Then you have reconstructed patches. So what we do is basically trying to snap the visual hull model to the reconstructed patches. So kind of step by step, we move each vertex on the visual hull towards the reconstructed patches, kind of snapping one by one with some regularization to get the final mesh model. Any question? Maybe a little bit not clear. Any questions for the part? So this is the final result I got for the object data sets. For each data set, you see one sample input image and a bunch of patches with texture mapped on and a mesh model. And let's see. So for this data set, there's some big concavity for the skull. And I guess many multi-phase tree algorithms have troubles handling this kind of huge concavity. But if you remember our algorithm, there's almost no regularization. It's kind of patch by patch, independent optimization. Then we can really easily handle those kind of huge depth changes or concavity. And so this is the actual human face without any projection. And actually, he happens to have nice freckles. And so actually, freckles help us matching features. And that's the reason why we pick him as a target. So if you have a really nice clean face without any texture, be nice makeup, maybe algorithm doesn't work. But for his data set, it looks pretty well and getting lots of details. And I'm going to show, some movies here. So again, we're getting the deep concavities for the skull data set. This is a relatively high resolution images, I guess maybe 2 megapixel, maybe 3 megapixel from 24 images. And on the right, you are looking at the kind of massive data set, probably one of the most big data sets I have worked on. This is from 48 images, and again, maybe 3 or 4 megapixel. I don't think I need 48 images to get kind of similar result, but I just took 48 images, so I just all over them. And you're looking at some of actually the full structure here. And I guess overall, you're not really making a big mistake, like this huge concavity you're getting right. But a couple of problems maybe here, and also there, the other side, you're not getting anything. So you get some fake structure. But this part is really difficult because it's like a cape going around the body. And to get the structure like here, you don't have many cameras looking at the surface because it's so deep. So you just didn't have many cameras looking at the structure, and we cannot do anything. You have at least 2 cameras look at the surface to the reconstruction. So we kind of gave up on this structure. But for all the other places, I guess, we are getting lots of details. And again, for my face and my body from 4 images. So you can see lots of our details on my face also. Like buttons, you can see here in a second. We can get really tiny details really well.
Did it not work well on your hair?
Oh yeah, for hairs, no. Yeah, 2 thin structures. Yeah, I think we can have, for thin structure, at least the width of the thin structure should be maybe 3 or 4 pixels to be handled. My hair is probably less than a pixel, and I just gave up.
So some of the specularities on the face, is that because you took enough? Well, there's only 4 images in this.
Yeah, 4 images, yeah.
So there wasn't much of an issue then with specularity?
For this, so in general, if you have specularities, specular highlights are treated as outlier.
Yeah.
So it works reasonably well. And for this data, I think I didn't have much specular highlights, maybe.
Yeah, it could just be really.
Yeah. So if you have,
a good.
I guess there are 2 images which does not contain specular highlights. For this, I work. I set the minimum number of images to be like a 2 to compute for the consistency for this data set. And let's see, for this body data set, I think you can see lots of details on my a shirt, even my nose and the mouth. And I thought that this data set is kind of difficult for the genes because it's a really black material which absorbs lots of light. And even with my eyes, I couldn't see nice texture here in this area, but seems to be working pretty well. So it looks like my algorithm is better than my eyes. I couldn't really see nice texture. Here's the second half of my data set. Not my data set. Some of them are coming from the other sources. Kind of scene data sets. So this are interesting in a sense that you have seen lots of water in the background. So water, appearance changes in every frame. So we expect this region to be kind of outlier, and we're not going to do any reconstruction for that place instead of creating garbages. And this is an artificial example for 7 images. I manually painted this kind of red human to each image. And this is actual data set from 3 images you have seen before with the pedestrians. And here's just pictures of our, again, sample input image and reconstructed patches and the mesh model. So for this example, I have some movie to show you later, but we didn't generate our kind of garbage for the water region. So the water has been detected as outlier, and we didn't generate anything, leaving just a hole, I think, which is a good thing, rather than generating garbages. And for this example, there are pedestrians all over, but to get, for example, to this reconstruction, we just use first and second by using a simple trick, ignore the third image. And to get this kind of to visualization, because we know that which image region contains obstacle. So when you do texture mapping, you just pick up the image which does not contain obstacle. So for this visualization, we can just remove pedestrians from the images. Just get the texture mapped textures of building. And so for this data set, 7 images, this is the result I got. So again, we can handle those outliers, obstacles pretty well. And one more experiment I have done is I replaced this 5th image by the 3rd without changing camera parameters, which means the whole 5th image becomes the garbage. Replace the whole texture without touching camera parameters. So we expect the algorithm to take the whole 5th image as an outlier, and also this red part as an outlier, but still use only consistent information to get some results. And this is the result I got. So again, you see more holes, because I guess there are simply not enough cameras looking at the corresponding structure. But I think we leave a hole instead of creating some garbages, I guess, which is a good thing. Yeah.
Images on the left, the grayscale ones, they were showing renderings of the oriented patches. Is that right?
So here, this is a texture map. You mean this image? Mm-hmm. This is a bunch of patches with a texture map done.
Texturing using the original color imagery?
Yeah.
I see.
So for each patch, you estimate a normal. So I just pick a camera which is going to face the front for each patch, looking at the normal and optical axis.
So there's no reconstructed surface yet, but it's splatting the patches.
Yeah, that's right. Yeah, because they are so dense, so it looks like our surface, but just a bunch of independent patches. So this is an example which contains water. Actually, you can see some false patches here, which probably corresponds to the water region, but there are not too many, so I guess our system can ignore most of the water region here. And in this example, it's from 3 images with a bunch of pedestrians, but we can kind of ignore those regions, pedestrians, then just use the right text to do texture mapping, and you are not seeing any people in this movie. And this is the data set from Christopher Storica from 7 images. Then this data set is kind of interesting in the sense that 3 or 4 images are taken far from the structure. And he has 2 or 3 images taken really close up. So you should expect, for example, he has close-up images for this structure. So you should expect higher resolution output for this structure, while low resolution structure for the other places. And our algorithm can have a built-in adaptive resolution output, because our problem basically tries to find a single patch in every beta by beta pixel cell. So if you have close-up images, you're trying to add more patches to that to the image. So our resolution is actually going to be higher. So our algorithm has an adaptive output resolution, which is kind of, I guess, rare for multi-view serial algorithm. Typically, for many algorithms, use voxels. It's kind of uniform like resolution. So which I guess one of the advantages of their approach. Okay, so this is the result without, I think, without replacing the fifth and third image, just a red human painted by me. So I have shown you like pictures, movies. Then people ask me, how accurate are they in reality, because they care about the actual accuracy. But thanks to Rick and Steve and Professor Corliss, there are some quantitative evaluation of multi-view stereo algorithm. And basically, they have these laser range scanner to get 3D model. They provide images, and we run our algorithm, submit results. They compare with the ground truth and tell you how accurate your model is. Then I've looked up the results webpage a few days ago, and it's been updated. But still, our algorithm is the best in terms of two categories, accuracy and completeness for 4 out of 6 data sets. I'm going to show you actually their website right now. So if you type in Google like a multi-view stereo, the first link is going to be this multi-view evaluation website. And so they provide like 6 data sets, actually 2 objects like temple. Actually, you have seen this object in the previous slide. 2 objects, and for each object, they have 3 different data sets. They are different in the number of input images. So for the temple data set, they have one data set consisting of only 16 images, and 47 or 312 images. And again, 3 different data sets for the dinosaur. And the algorithm I just explained is, let's see, this Furukawa 2. Then you're looking at for each data set, and for each method, you're looking at 2 numbers. The blue numbers is pretty much accuracy, or distance between your model and the ground truth. So the smaller, the better. And for green number, it's kind of completeness, how much your model can cover the ground truth model. And the larger, the better. So if you look at the numbers, I think our result is the best for this object and this object and this data set, this data set, these 4. And we are doing, I think, pretty good on these 2 remaining data sets as well. And one thing to note is, so for this dinosaur data set, if you remember our results in the previous slide, some white dinosaur without much texture. Our result on the smallest data set here, consisting of probably 15 or 16 images here, is actually better than any other result in the whole table, except ours here and there, which means our result for 16 data sets, 16 images, is better than any other algorithm using the whole 363 images. I guess which is pretty surprising that you can tell how good our algorithm is. You can really good reconstruction from only a few set of images. Oops. Oh, I have one more thing to show. So these numbers are actually really tricky. Most people, I think, go to this website, look at the numbers, and tell, oh, this is good, this is bad. But they also provide some rendered views. For example, for this data set, so we have currently the best numbers, and the second best result is our Vogiatis 2. This method, but if you just look up the reconstructions, so here is left, you're looking at our reconstruction. Then left is their reconstruction, Vogiatis et al. Then, for example, this structure, they're not getting the right, while you're getting this kind of sharp concavity. And also, their result seems to be pretty kind of noisy, like around here. And also from a different viewpoint, should be actually the other way. So this is our reconstruction. And this is their reconstruction. So they are not getting the structure here, concavity. While their result has really good numbers. So I guess you should also look up the actual views, rendered views, to look up the results of this evaluation. So this is again another rendered views of our algorithm, and our top performers are. Let's see. So again, I think it is pretty difficult to get like structure here, this sharp concavity for the other methods. And even qualitatively, I think our result looks, I think, better than the other. Maybe this one actually also looks pretty good, but not getting the structure right as here. So I'd like to mention as a summary kind of contributions of this approach. And first of all, the accuracy, as you have seen the quantitative evaluations. But I guess this one could be actually misleading for many people who look up this multi-view stereo. Just look up numbers and good and bad. And I think there's more important factors kind of hidden, which I want to emphasize here. So one advantage of our approach is we do not need any additional like a secret input. So many methods typically are use like a bounding box, kind of start with, or maybe visual hull model or some depth ranges if you want to do some depth labeling approach. And our approach doesn't need anything, just camera parameters and the images. We just get the result, which is actually useful for people who are not like expert in computer vision. If you think about like providing software to people. Then another advantage is this is a really general algorithm. You can handle like object-like datasets or scene-like datasets, while some methods just focus on objects. But still, we can do better than all the other methods, which may be just focus on object datasets. So I guess this is also another advantage, kind of the flexibility of patch-based surface model. Another thing is due to the kind of weak regularization, we can handle like complex structures. I haven't seen many other algorithms which can handle like a deep concavity. So I would say this is also another advantage. Again, occlusion handling. This was just a simple trick. I guess any method can just use the same trick, and use into their system to use. But I guess we are kind of the first to show that we can really handle like severe occlusions by a simple trick. Then the last thing is an adaptive output resolution. If you have close-up images, the reconstruction is going to be higher for that place. I guess this is also kind of advantage of like a patch-based model. You don't really have to care about kind of adaptiveness. It's kind of built in like a scheme. Yeah.
Is the location of the patches in 3D dependent on which image you choose to dice up into your beta?
Mm-hmm. Well, let's see. So suppose you have a patch which is between 3 cameras. Then so one is kind of close, one is far from it.
Right.
But if you look at the close camera, then you see kind of cell which is empty. Mm-hmm. So even though we have like different images in different scale,
right,
there is always an empty cell in the closest image. So we are trying to add patches to that place. Is it answering the question?
I think so, but the ones that are far away will have several patches in a cell, and that's
that's right. Yeah, that's okay. Yeah, yes, at least a single patch in every bit of it's a cell. Yeah. So here's some future work or extension of this work I've been thinking and I've been working on. First of all, so we've been just working on like static frame reconstruction so far, but maybe we can do some motion reconstruction or motion recovery. And so the framework, we have multiple synchronized video cameras instead of multiple static cameras. So you move around. And you want to capture structure frame by frame and also get some motion information altogether. You're kind of adding a temporal component to our patch-based model. And I have some results to show in a movie. Let's see. Here. Oh, yeah, here. Oops. Okay. So for the dataset we've been working with, we just borrowed our dataset from one of the SIGGRAPH papers this year. The group by Professor David Forsyth, Ryan White, and the Keenan Crane, David Forsyth. So their purpose is to capture this kind of cloth motion. And so design these special triangle patterns. And in their approach, they're looking at the triangle, like red, or special, kind of color coding, kind of blue or red or yellow. If they look at the colors, they actually know where those triangles should be because they have the whole knowledge of where our triangles are printed. But in this work, we just wanted to show that you don't have to store that knowledge. You just use multi-view constraints to get our reconstruction and also motion recovered. So this is kind of the output of the raw output of the result. So we kind of pretty much get a bunch of patches in the first frame. So a bunch of patches. We try to track those patches frame by frame. Maybe adding more patches and also handling occlusions. So this is the raw output of our result. So each patch is actually existing frame, is tracked frame by frame. And so let me show it again. Maybe around here. Yeah. So this is just our reconstructed patch with the texture mapped on. And because we track patches, we can essentially getting velocity field, like translational or rotational velocity field. Actually, both we are getting. And if you know the velocity field, actually it's kind of hard to see here. But you can kind of animate your mesh like here. This is a mesh model, same topology in all the frames, kind of moving around according to the velocity field. then I guess you can see in this frame we can handle occlusions. For example, here in the first frame you see some holes. He was holding a pants with our right hand. So we are not looking at the surface. So initially you don't have any patches, but we can handle occlusion. We can fill in the patches where the surface becomes visible, and etc. So I guess this result basically says that if you have some texture on your object, then even if the geometry is really complex, really fast motions, you can get the structure and also motion that recovered right. And the last thing I want to show is it's another kind of future work which might be interesting. So this is a movie I showed you earlier. So in this example, you have 3 images originally and pedestrians. But our algorithm basically tells you that we can detect image regions which contain obstacle. So we are really good at telling which is the structure like behind and which is the obstacle. So maybe you get some movies, like a building with lots of people. So you kind of imagine painting, but using multi-view constraints to like image in painting to remove people. And maybe there's some movie editing software by using that tool to do something interesting. And I'd like to thank a lot of people to complete this work. And yeah, thank you very much for the attention. I'm happy to answer any questions.
Thank you. Questions?
So I can see this step from patches to surface. Sometimes remove stuff, sometimes add stuff.
Yes.
How do you handle the topology, etc.?
You mean adding, for example, missing places, adding the holes? You mean?
Yeah. What exactly is happening there? How are you deciding on the surface topology?
I see. Oh, so in the snapping framework, so we need a mesh model, and what we do is basically for each vertex, and we have the estimated normal from the mesh. They kind of find the reconstructed patch which is along the normal. So you know how much this vertex should be moved inward or outward. So we move this vertex little by little with some regularization. So it's okay that there's no patches reconstructed, some hole. So it's going to be just snapped because there's no patches, only regularization works. So you get some smooth surface. Just kind of way to kind of add more information, kind of filling holes. And I don't think there's also a mechanism to kind of remove information from patches. So suppose you have some incorrect patch here. You have a bunch of correct patches. So when trying to kind of snap the surface, because there's only a single incorrect patch, but so dense correct patches, so we kind of ignore this patch because so many patches here, incorrect patch here. So we know that this is the right structure. So there's some kind of.
But how do you join up the patches in the first place? Do you search along the surface?
You mean how to compute correspondence between patches and the surface?
You basically have an assortment of patches.
Yeah,
It's already
so
on the surface. How do you
yes.
decide?
So see, that's a good question. So suppose you have a set of patches and you have a mesh model. So you want to compute for each patch. You want to know the corresponding the vertex on the mesh. Does it make sense? So you want to know the correspondence between the mesh model.
Well, if you had a mesh in the first place,
Yeah.
you've put in the first mesh then. How do you get? There's some initial choice of mesh.
Oh, so it could be one of 3 methods. So it could be visual hull model. You have a segmentation, program background segmentation. You use a visual hull model for most of the object data sets. For scene data set, like a building, there's no segmentation information. We can't get a visual hull model. So I just use the convex hull of reconstructed patches. You have a bunch of patches. I just use the convex hull to initialize a mesh model. So I do some edge splitting, kind of remeshing algorithm to make it dense, and do some snapping.
Would you say it's similar to like a level set started around the whole, and they usually look like that?
Yeah, but using the information of patches, so you don't really worry about local minima because you have patches reconstructed. So just compute for each vertex on the mesh how much you have to go further. Do some regularization here.
So for the temple data set, you started with a visual hull?
Temple data set, yes, visual hull model, yeah. But actually really bad visual hull model because for that evaluation, they didn't allow me to do any manual work. So I used first of all, that data set, the background is black. So I first used the dark color should be background. Then I used some morphological operation, erosion, delation, to get a really bad segmentation. So I didn't really get a good visual hull model. So I have a reasonably good mesh model to start with. And so the mesh model doesn't have to be really good to start with because we have all the patches reconstructed. And if you think of a convex hull of all the reconstructed patches, they're really bad. but because we have all the information recovered, and snapping is actually pretty robust. So initialization doesn't really actually influence the final result.
What would have the wrong topology? You wouldn't be able to introduce the gaps between the.
Oh, you mean, for example, like holes? That's a really good question. Actually, in iterative snapping, I have some like hacky algorithm to kind of remove holes, or I allow some kind of topological changes. So there's some work at ECCV a couple of years ago, which can mesh-based topology changes. So if you keep on moving vertices, if the like a structure becomes too thin, and cut it open. So there's some kind of heuristic ways to kind of handle topological changes. But I actually didn't see any like problem in getting the structure.
Maybe related to Rick's early work on oriented particles.
Right, so the oriented particles was a way, and now I think what Mark's doing with the moving least squares and things like that, right, is related to that, right? But the technique you developed with Kazdan, right, that Poisson technique with the indicator function, does that generate a surface from a random collection of oriented points? Right. And you are using Kazdan's technique?
Yeah, actually, yeah, for some of the experiments, and I've been using his old version, which didn't work well for our like relief structure buildings. So I just ended up using my own implementation. But one thing I like to claim is the core algorithm is getting patches. So from patches to surface is a different category. So I guess that is one part which should be improved a lot. So of course you can use your algorithm to go from patches to surfaces. So right now I must admit that our way of getting a mesh model from patches is really hacky. So I don't think that's really a nice way to do. So I like to say that getting a patch is really important, and this is where we've been working on.
What happens when you have a textureless area?
Yeah.
Is the end result a little noisy, or does it kind of just look
nice? Yeah, it's a really good question. So one of the data set, if you remember the white dinosaur model, which has been used for a multi-view stereo evaluation, right here. So I guess this is an object which doesn't have much texture, I would say.
It still has a gradient.
Yes, yeah, that's right. Then there is.
And that's variable inversion, if I remember correctly.
Sorry?
Because that's from your data set, right?
Yeah, that's right.
So
then actually there is some area on this dinosaur model which is probably really textureless or no texture. And any method I have seen has a trouble getting actually the right shoulder, the other side of this picture. It looks like any method couldn't get any structure right. And actually in our result, reconstructed patches, it's here. Here you are not getting any patches. This is a place where everybody has a trouble. But we are not generating any patches here. So again, something wrong happened.
So
so kind of similar regularization. Yeah.
Okay.
But I guess this is because there's no good information, so we are not really.
So why aren't you getting any information there? Because it is the occlusion should say that everything agrees. Why do you get no information?
So suppose you have the just solid color, no intensity differences. What we use is a normalized cross correlation.
Yeah.
So suppose you have almost intensity like 255 or 254. Yeah. So because we normalize variance and the average, so variance becomes make everything really noisy. Actually, you get that value if you don't have really nice texture.
Okay.
There is a way to improve normalized cross correlation, which Andrew Blake and Antonio Parisi did, which is you never allow the gain to go beyond a certain amount, so you don't amplify noise.
I see, yeah.
So even if your variance is very low, you basically add a baseline to that variance, and
I see, yeah.
that just prevents that blow up of the noise.
Yeah, I think that's a good point. So I use just normalized cross correlation to compute our similarity of image regions, and I think we should really study actually more what is the right function to use. And people in general in multi-view stereo tend to just pick normalized cross correlation without really thinking about the good or bad effects. I think that's the one thing we really need to actually study and know what really causes the problem, in the reconstruction.
Any other questions? Okay, we're going to go for lunch now in the cafeteria.
Yeah, thank you very much.
Okay, thanks again.
Yeah.